A robot video goes viral because the motion looks human. The harder question is, what had to work in the real world for that 10-second clip to happen at all? Today, we unpack the mechanical story behind the demo, shifting focus from AI intelligence to the physical bottleneck of dexterity and actuation speed. We are looking at why the hardware limits what these machines can actually do, regardless of how smart their software becomes. There is a persistent myth in popular discourse that if we just make the brain big enough, the body will follow automatically. This narrative suggests that once an algorithm learns to manipulate objects, the robot instantly gains human-level capability. But this view ignores the fundamental physics governing mechanical systems. It treats robots as purely digital entities when they are, by definition, physical machines subject to gravity, friction, and material limits. To understand where humanoid robotics is actually heading, we must separate the computational promise from the engineering reality of actuation speed and dexterity constraints. Consider the sheer scale of data required for a system like Captain in neutrino physics, which instruments 5 tons of fluid with over 2,000 readout channels to capture rare events. This analogy helps us understand why physical systems are so much harder than software simulations. In robotics, every degree of freedom requires its own set of sensors and actuators working in perfect synchronization. The challenge is not just processing power, it is the mechanical bandwidth required to move heavy limbs quickly without destroying them or their surroundings. When a robot attempts a complex manipulation task, the delay between sensing an object's position and moving a finger to grasp it is dictated by motor response times, gear backlash, and thermal limits in the joints. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This creates a hard ceiling on what we call dexterity. A human hand can adjust its grip with micro-movements that happen faster than most control loops can sample. In current humanoid designs, actuation speed often lags behind these biological reflexes. If you are trying to catch a falling object or manipulate a delicate part without crushing it, the robot must react in milliseconds. However, many high-torque actuators used for walking and lifting simply cannot accelerate fast enough to match human hand speeds. The result is a system that moves with deliberate caution rather than fluid adaptability. It can lift heavy boxes because the motors are built for torque, but they struggle with speed because of inertia and safety margins built into the control software. The bottleneck becomes even more apparent when we look at energy efficiency and thermal management. Just as neutrino detectors must manage thousands of channels to avoid signal noise, a robot's joints generate significant heat during rapid movement. If an actuator tries to move too fast or with too much force for its size, it overheats quickly. This forces the system to throttle down, reducing speed and precision exactly when dexterity is most needed. We see this in real-world deployments where robots that perform well on a factory floor at slow speeds become unreliable during faster operations. The mechanical design prioritizes strength over agility, creating a machine that feels clumsy when asked to do something requiring fine motor skills. This gap between intelligence and mechanics explains why we have not yet seen widespread adoption of humanoid robots in complex, unstructured environments. We are building brains that can reason about tasks, but attaching them to bodies that cannot execute those tasks with the necessary speed or precision. The software may know exactly how to pour a glass, but if the actuator takes too long to react to the weight of the liquid shifting, the robot will spill it. This is not an AI problem. It is a control theory and mechanical engineering problem. It requires new materials, faster actuators, and better thermal designs that have yet to reach mass production standards suitable for general-purpose robots. We must also consider the constraints imposed by safety regulations in human-adjacent spaces. To ensure no harm comes to people working alongside these machines, systems are often programmed with conservative limits on speed and force. While necessary for public trust, this further reduces their operational dexterity compared to a human worker who can intuitively gauge risk through touch and proprioception. The robot cannot feel the slip of an object until its sensors register it, by which time the damage may already be done or the motion must stop abruptly. This reactive nature is fundamentally different from the predictive capabilities humans use daily. The path forward requires a shift in how we approach robotic design. Instead of focusing solely on improving neural networks to handle more complex tasks, engineers need to invest heavily in mechanical systems that can keep up with those cognitive gains. We need actuators that are lighter yet stronger, capable of faster response times without overheating. Until the physical hardware matches the speed and dexterity required for real-world work, these robots will remain limited to highly constrained environments or low-speed tasks where their slowness is not a liability. The story of Captain Clark serves as a reminder that even with advanced planning, mechanical bottlenecks can stall progress just as effectively as software bugs. We are currently in an era where we have the intelligence but lack the physical tools to fully realize it. The future of robotics depends on solving these actuation and dexterity challenges so that machines can move as fluidly as they think. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.